Every time you tap a screen, send a message, or watch a video, you trigger a global system that never sleeps. The internet connects billions of people, businesses, and machines every second. It powers homes, transportation, hospitals, and entire economies. Most of the time, it feels invisible until something breaks. A slow connection, a blackout, or a major outage can bring whole neighborhoods and businesses to a stop. This system decides how fast information moves, who can communicate, and how the modern world functions. To understand today's world, you first need to understand how the internet actually works.
The internet is not an invisible cloud floating in the air. It is a massive physical system built from real materials. Beneath cities, streets, and buildings, fiber optic cables carry data as pulses of light. These cables run through neighborhoods, across countries, and under oceans. Inside telecom buildings, racks of network gear push traffic forward every second. Data centers hold thousands of servers that need electricity, cooling, and security. Even wireless internet depends on wires once your signal leaves your phone and enters a router. Every search, message, or stream relies on cables staying intact and powered. When construction crews cut a cable or storms damage a line, service slows or drops. The internet feels invisible only because its physical parts are hidden in walls, ducts, and sealed buildings.
When you open a website, your device first joins a local network. Your phone connects to Wi-Fi or your computer plugs into Ethernet. The router becomes the traffic manager for everything inside your home or office. It gives your device a local IP address so it can be identified on that local network. At the same time, your router talks to the modem or fiber terminal that links your building to the outside provider. Your device then creates a request, like "load this web page," and the router prepares to send it outward. At this stage, your data has not crossed the city yet. It's still inside your local network, moving only a few meters between device, router, and modem. This local step matters because weak Wi-Fi, bad cables, or overloaded routers can slow everything before the internet even begins. After your router has a request ready, it hands the data to your Internet Service Provider, or ISP. In many homes, the modem or fiber terminal converts the router's digital traffic into signals suited for the ISP line. That line might be fiber, cable, or older copper infrastructure. Your building connects to a neighborhood cabinet, and that cabinet connects to larger ISP equipment. From there, your packets officially enter shared public networks used by many customers at once. The ISP watches traffic levels, manages capacity, and routes your data toward the broader internet. If the neighborhood node is overloaded at peak hours, you feel slowdowns even with a good plan. This is the moment your private home network becomes part of a city-scale system. One small request now travels through equipment owned and maintained by the provider, not by you. Before your device can reach a website, it must find the destination address. Humans type names like example.com, but networks use IP addresses like numbers. This translation is done by DNS, Domain Name System. Your device asks a DNS server what IP address matches this domain. If the answer is cached, it comes back quickly. If not, the DNS server contacts other DNS servers in a chain until it finds the correct record. Once your device receives the IP address, it can send packets toward the right server. DNS is like the internet's phone book, and if DNS is slow or blocked, websites may fail even if your connection is strong. Many outages look like the internet is down, when the real problem is DNS not returning the address your device needs.
Your request does not travel as one big file. It gets split into small packets, each carrying a piece of data plus addressing information. Packet headers include where the packet came from, where it's going, and how it should be handled. These packets can take different routes depending on congestion, outages, or routing policies. If one path is busy, packets may detour through another city or provider. Some packets may arrive out of order, but the receiving system reassembles them correctly. If packets are lost, they can be retransmitted. This packet approach is one reason the internet scales. Millions of different conversations share the same physical links. For you, it feels like a single smooth stream. Under the hood, it's a constant flow of tiny pieces moving independently, like traffic in a huge road network with many lanes and exits.
Routers are the internet's traffic directors. Each router reads the destination IP address on a packet and decides the next hop, where that packet should go next. This happens in milliseconds, millions of times per second. Large routers sit inside ISP cores and Internet Exchange Points, or IXPs, where many networks connect and swap traffic. At an exchange, your ISP can hand packets to another network that is closer to the destination. Routers update routing tables constantly, learning which paths are available and which are failing. If a fiber line is cut, routers redirect traffic to working routes. This is why the internet often keeps running during local damage. But if a major exchange or core route is overloaded, delays spread widely. Routers don't store your data, they forward it quickly, like a conveyor belt system designed for speed and redundancy.
When your packets need to cross long distances, they ride on high-capacity backbone networks. These are thick fiber routes built for massive traffic between cities and countries. For international connections, most data travels through undersea fiber optic cables laid on the ocean floor. These cables connect continents through landing stations on coastlines, then continue into inland fiber networks. Along the way, signals are boosted by repeaters and amplified equipment to keep data strong across thousands of kilometers. Satellites exist, but they are used mostly for remote areas and special cases because they add more delay. Undersea cable problems can affect whole regions, especially if multiple cables share the same landing area. This global layer is the reason a video can stream from another continent in seconds. It's also why the internet depends on ships, maintenance teams, and physical protection for cables underwater.
Eventually, your packets arrive at the destination network where the website or app is hosted. Most services run inside data centers, large facilities filled with servers, storage, and networking gear. A front-end load balancer receives incoming requests and decides which server should handle them, spreading traffic so no single machine collapses. The server processes your request. It may fetch a web page file, query a database, or start sending video chunks. Many big services use content delivery networks, or CDNs, which store copies of popular content in data centers closer to users. That reduces delay and lowers long-distance traffic. The data center also needs strong power systems, backup generators, cooling, and security controls. When a data center has trouble, power failure, cooling failure, or software errors, users notice instantly as slow loads, buffering, or error pages, even though the rest of the internet still works. After the server creates a response, the internet sends it back to you as packets. The return path may be different from the outgoing path because routing changes based on congestion and policy. Your ISP receives the packets, forwards them through the neighborhood node, and sends them into your home line. Your modem or fiber terminal passes them to the router, and the router delivers them to your device. Your device reassembles the packets into the web page, message, or video stream you see. The total time for a request to go out and come back is called latency, often measured in milliseconds. Lower latency feels instant, especially for gaming and video calls. Higher latency feels like lag, even if download speed looks fine. Distance, congestion, and server location all affect latency. That's why a nearby CDN can make a page feel fast, even on average internet.
The internet survives because it is decentralized and redundant. There is no single master switch that controls everything. Instead, thousands of networks connect through many exchanges and backbone routes. If one cable is cut, traffic can reroute through other cables. If one data center fails, services can shift to another region. Providers build backups,
duplicate links, spare equipment, and alternative power. But resilience has limits. Local outages happen when a neighborhood node fails, a router crashes, or power goes down. Larger outages happen when major backbone routes are overloaded or when configuration mistakes spread across networks. Still, the design favors recovery. Packets keep flowing along the best available paths, and routing protocols help networks adapt quickly. That is why your internet can feel always on, even though parts of the system break every day. Stability is not luck, it's engineering, redundancy, and constant maintenance.
So, the internet isn't magic, and it isn't a floating cloud. It's a real, physical system of cables, routers, exchanges, and data centers working together every second. Your click becomes packets, packets find routes, servers respond, and everything returns to your screen in milliseconds. Once you see the system, you start noticing what can slow it down and what keeps it running. Next, a bigger question. What happens when millions of people all demand the same content at the same time?